Joint truth tables. An introduction. So what are joint truth tables? Well, let's contrast them with the normal truth table, which breaks up one sentence into its constituent parts to demonstrate the conditions under which that sentence is true or false. A joint truth table works a little differently. It shows multiple separate sentences. Yes, breaking them up into their parts. These sentences are the premises and conclusion of some argument. The purpose of a joint truth table is not to determine whether any given sentence is true or false, but whether the whole argument is valid or invalid. You could think of a joint truth table as several truth tables of the normal kind, all put together in one. So let's contrast this with a regular truth table, since if you're having trouble with those, you're going to have a lot of trouble with joint truth tables. In a regular truth table, we want to put every constituent part seen in this sentence into the truth table. Here we've got not Q and we've got not P, so we put those in. The next part is Q or P. We're going to go ahead and put that into the truth table. The next longest sentence is not Q and Q or P. We continue to get longer with this messy looking conditional. Finally, we put in the whole sentence. This is what we're solving for after all. The truth of this entire sentence with the main connective of the V. But we've got to do all the parts in between to figure that out. So, for each column, we're looking at one main operator of the column. Here, the main operator is not, and our input is P. So we look at the P column, we apply the operator not, and we put in the answers for the truth table. Same thing at the next one, but with a different input, Q. For the third column that we have to fill out, V is our operator, and we look at both the Q and P columns as the input to determine our output in truths and falses. This next one gets us away from using the two basic P and Q. Instead, we'll look at the Q or P column and the not P column. We'll use those for our inputs, and we'll use ampersand, or and, for our operator. That's going to get us false, false, true, false. Now, we use the column that we just made as one of our inputs, along with not Q, and we apply conditional. That gets us our truth and falsehood outputs. And finally, we use P, or, and the long conditional that we just evaluated as our inputs and operator. And that gets us true, 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 false. That's our answer. Those are the truth and falsity conditions. Or not conditions, but results for that truth table. So this truth table tells us which inputs, truth values for P and Q, make this sentence true, and which make it false. The yellow show the inputs that give us true output, and the green show the inputs that give us false output. Since this sentence is true under some inputs and false under others, it is contingent. We've evaluated just one long sentence. All that really matters is the last column. Each other column there is just there to help us figure it out. In a joint truth table, however, multiple columns will be relevant. So let's look at one of those now. Follow these steps to test an argument for validity with a joint truth table. Number 1, put each premise and the conclusion into a truth table. Break them up if they have more than one operator. Number 2, note which columns are premises and which is the conclusion, and which ones are just parts. Then fill out truth table like normal with the true and false outputs. Step 4 is where it gets different. Highlight each row with all true premises. You can now ignore the other rows. Look at each column for the conclusion. Look at the only column for the conclusion, rather. If it is true in every row with all true premises, remember, you're forgetting about the others, the argument is valid. If it is false in even one row with all true premises, the argument is invalid. It only takes one time, one false, in a row where the premises are all true, for the argument to be invalid. This is a counterexample. We've found those with arguments in English plenty of times, and now we're doing it with a truth table in symbolic logic. So let's put these steps to use in a really simple truth table. Well, simple for a joint truth table. Step 1, put the premise and conclusion into the truth table. Break them up if they have more than one operator. Premise 1 does have more than one operator, so we've got a row for not P, or a column rather, sorry. We've got a column for P or Q, and we've got a column for if P or Q, then not P. Premise 2 is just Q. It's already there in the table, so we don't need to do anything. Premise 3, conclusion, not P, is also already there in our truth table, since it was part of premise 1, so we don't need to do anything. If you want to, you could make another column on the end, just for clarity, but it's not required. Step 2, note which columns are premises and which is the conclusion, which are just parts. Premise 1 is our last column, premise 2 is Q, and our conclusion is not P. P or Q is just a part. We won't be concerned with its truth or falsity after we're done filling out the truth table. We fill in the values for not P, P or Q, and for our last column, premise 1. Then we highlight each row with all true premises. The third row has all true premises. Remember, we're only looking at the second column with Q and the last column with P, if P or Q, then not P. The fact that it's true in P or Q, that doesn't matter. Then we look at the column for the conclusion. If it is true in every row with all true premises, then the argument is valid. There's only one row with all true premises, so it's pretty easy to check this one. And sure enough, that one ends up being true. Because that cell lists true, this argument is valid. Every time you've got all true premises, you end up with a true conclusion. Let's take a look at a somewhat more complicated argument. Premise 1, and premise 2, and the conclusion have all been put into that, and we've broken them up because they do contain more than one logical operator. We aren't going to take the time to go through every step because this part really isn't any different to doing a regular truth table. Now we're noting which columns are premises and which is the conclusion. So, of our columns, we've got premise 1 in either not P, or Q. We've labeled premise 2 over the column with if Q, then P or not Q. And our last column is our conclusion, either Q or not P and Q. Then we fill out the truth table, just like normal. This would take quite a lot of time to put in the video, so I hope you'll trust me that I've got the answers right. If not, go ahead and pause and do it yourself. Step 4, highlight each row with all true premises, ignoring the others. Well, the only time premise 1 and premise 2 are both true is in the last line. So that's the only one we highlight. We can forget about the first 3 rows. Then we look at the column for the conclusion. If it's true in every row with all true premises, it's valid. If it's false in even one row, it's invalid. Well, here's our only highlighted row, and it comes out false. This one is invalid. Even if there were another row with all true premises and a true conclusion, the argument would still be invalid, because it only takes one instance of false conclusion and true premises is enough to make any argument invalid. And this one is. Doing joint truth tables can be kind of time consuming. It can be a little tricky. However, it's completely foolproof. If you follow these steps correctly and fill out your truth table correctly, of course, you will definitely be able to find whether or not an argument is valid or invalid.